All right, Ampere's law and the force between two parallel current carrying conductors, which is seems kind of like an obscure thing, but it actually is pretty historically significant, as you'll see. So the strength of the magnetic field around a current carrying conductor. Remember, you mentioned I showed you before that Oersted was the person that just noticed that magnetic compasses, magnetic field lines were created by current carrying conductors. He noticed that compasses would change position depending on which way the current was going or if there was current going. So that was a big discovery, of course, right? He went on to look into it and found that the magnetic field was, of course, proportional to the amount of current, and it was inversely proportional to the distance to the current carrying conductor. Um, and so basically, um, found. Oh yeah. So if you combine those two things, it just looks like a one to me there. So basically proportional to the current divided by the distance away, right? So we have this kind of relationship. Well, later on, Andre Marie Ampere developed a general relationship between any current carrying conductor. Was inspired by that and thought, geez, I can look into this further, right? So it's called Ampere's law. So it reads like this, right? Along any closed path through a magnetic field, the sum of the products of the scalar component of the magnetic field parallel to the path segment is directly proportional to the net electric current, right? So, and net electric current passing through that enclosed path, right? So written mathematically, it looks like this. So this is the sum of, and there's your magnetic field parallel to the path length and so on. And then there's your proportionality constant and the current, right? So proportional to the current. So yeah, we got that. We've got our little path length pieces. We've got the sum of all the parts. We've got our proportionality constant, which is sometimes called the permeability free space, right? It's just 4 pi times 10 to the negative 7 number, which came from previous work as well. So that permeability of free space thing is calibrated based on those two wires that I'm going to talk about shortly. Yeah, so basically it's a general relationship that can be used to determine the magnetic field strength in any situation, not just straight conductors. So to see that this works, let's look at a simple case. We're going to use a circle for our circular path, our closed path, because then we have some geometry that we know to do with that. And so we have this, again, also, this makes it a constant magnetic field, right? Because we're the same distance away from that wire the whole time, which is another simplification that makes the circle preferable for this case. So we've got really this. So if we're adding up all the path lengths, that would, of course, be the circumference. There's the geometry I was talking about, right? So we end up with this equation for magnetic fields around a straight conductor. And our K value is that mu naught over 2 pi business. Really, the same proportionality constant and relationship that Oersted determined, of course, if you notice, right? An application about this, I'm going to skip the first part here because the main event here is how coax cables work. If you're not familiar with a coax cable, it's an old school television cable. It's really one of the uses for it anyways. It's used all over the place. But it has one of the conductors is like in a braid, like a mesh. You see it here. And it surrounds the entire inner wire. So the inner wire is a solid or stranded, but I mean a core of a conductor with a conductor that surrounds it. So if we imagine a circular path that's outside of the cable, well, the net current is zero because there's current going one way and the other way, and they cancel each other out, right? So coax cables shield against external electric fields, but they also shield their own magnetic fields because, according to Ampere's law, right, the sum or the amount of current is zero, and so the magnetic field effect is going to be zero. Pretty neat. Another application of Ampere's law. So we've got a solenoid or a coil of wire. And so in this coil of wire, picture the wire going around and around and around. And so the current's going out here and in and out and in and out and in. That's what you're looking at there, sort of a diagram of like a cross section of it. So along paths WX and YZ, the magnetic field is perpendicular, right? The paths along WZ and YZ. The magnetic field shown in arrow is perpendicular to the magnetic field, and therefore the magnetic field is zero along those paths, right? So there's no component parallel to the path. So recall the magnetic field outside is zero, so WZ is going to be zero. And so finally, the magnetic field inside here along XZ is parallel to the path. Just pause for 1 sec here. I've got a phone call coming in. All right, so where was I? I think the magnetic field line in this region is parallel to the path length, right? So yeah, it counts basically, right? So you add that up and so on. So only the contributions for the total field strength come from that path, which is L, because this thing is like L long, if you will. Yeah, so the amount of current is going to be N times the current times the number. Sorry, the number of the number of coils, right? Turns of the conductor gives you the amount of current that you're getting in that spot. So yeah, there's the magnetic field for a coiled conductor, for a solenoid. So you can see that Ampere's law is kind of abstract, but it allows you to develop meaningful equations that represent actual magnetic fields, right? And it's just obviously a typical, just use the formula. It's to do with the concept at hand here. So we've got a solenoid, and so you're using the solenoid formula. Watch for like the number of turns of the solenoid, right? That's a key to notice. Like, oh, you've got 300 turns. Okay, well, you're going to do the equation with N in it for the number of turns, of course, right? And you just plug the numbers in and do the calculations. Okay, so it gives you the magnetic field strength. So the historically significant thing here, just for how things were sort of developed and originally and all that, is the idea of what happens if you have two current carrying conductors side by side. So you can see here, if the currents are in the same direction, then we're going to have a down magnetic field. Use your left hand for electron flow, right? You've got this magnetic field that curls. Your thumb's pointing to the left. Your fingers are curled towards you. Visualize or do that with your hand, So your hand's going up. Your fingers are curling up in behind and then down in front of a wire. If you put a pencil in the palm of your hand, there's the wire and your fingers are curling up and around it, right, towards you. So anyways, magnetic field's down on there, and the magnetic field on the inside and the other side is up. So we have opposite magnetic fields, and so these two wires would attract. And then if the current was going the opposite, if the currents or electron flows were going the opposite way, there'd be repulsion. Okay, so analyzing this, what would the magnetic force be? Well, it's going to be proportional to the amount of currents. It's going to be proportional to the amount of wire length and so on, and it's going to be inversely proportional to the distance, right? If you actually experimentally figure that, check this, that's what turns out to be the case. Fairly logical. The only thing that could have been, I would say here, is experimentally that could have been an inverse square or something like 1 over d squared, but turns out it's 1 over d. So that gives you an equation essentially, because you have the concept of proportionality, and then the proportionality constant. You can think of figure out what that would be, right? Well, what they did, this is the historically significant part, is they chose to calibrate this so that 1 amp of current is the current that makes there be 2 times 10 to the negative 7 newtons of force, which is a very obscure number, but obviously it's made to match previous work. With this sort of matches along with this 4 pi times 10 to the negative 7 permeability of free space number, right? So that gets rid of the 10 to the 7 and drops this down to being just a 2 pi, which kind of, you'll see it happen in the calculations when you're doing it if you want to simplify it instead of calculating all the numbers. Yeah, so if a different proportionality constant was chosen, then we'd be, our units for amps would be much different. That's all. We'd be used to working with different sort of calibers of amperage in circuits. So there's a summary of that stuff. So again, we have a question to do with, force between wires and so on. So you use the force between wires equation, plug the numbers in, and you get the answer. Okay. And then the last part. Sometimes they talk about force per length. So if you divide out that length, if you're asked for force per length, lengths would have canceled out and would have had, very similar work. It just would have been newtons per meter instead of actual newtons, right? Which is pretty common because length. Wires can be any length and so on. And if you're interested in the total amount of force, you can just multiply out to get the total force, depending on how much wire you use. So yeah, so that is Ampere's law and force between two parallel current carrying conductors, and your practice questions. And as always, let me know if you have any questions. And until next time, see you later.